So we learned how to compile the code, we learned what kind of problem we want to solve. It's this problem here of a beam on 3 supports with an imposed displacement in the top L/5 particles in the center. Now it's time to implement this problem as an input file for the DETO2D code. To do this, we double-click on the input file, input.dat, which opens this text file which you can edit with any editor like a WordPad in Windows or text editor, you name it. First line tells you that everything starting with the hashtag is a comment, so you can write whatever you want, place them wherever you want, there will be whatever comes after the hashtag will be disregarded. Second line is just a note to make sure that you are consistent with units of measure. So you could use whatever units you want in your examples. For example, if you work with large structures, maybe you want to use the international system, where lengths are in meters, masses are in kilograms, and time is in seconds. And if you do that, then you have to be careful that any other unit, a quantity that requires a unit in the script, must be expressed in the same international system, and everything that you take out as an output will be expressed in the international system. In this example here, we will not use the international system, we will use this system here. We will express the units of length as millimeters, as you already saw from the example up there. We will use as a unit of mass the grams. We will use as a unit of time the microseconds, which are 10 to the minus 6 seconds. And if you work out from here what is the unit of force is mass times unit of length over unit of time to the power 2, and this works out to be kilonewtons. Okay, so everything in this example will be expressed in this set of units. But you can work with whatever other kind of units. So for instance, if you use U of L equal meters, so international system, unit of mass equal kilograms, a unit of time equals seconds, then you will see that the unit of force will be kilograms meter over square second, which is Newton, for example. So going back to our input file here, this is just a note for you to remember, be consistent with the units. Then the next line is the first line without a comment is this geometry. This is a command that is read by the code. So when the code reads geometry, it takes these as inputs and sets them into the software itself. What are these? Well, these are the number of elements, number of particles that we use to discretize the horizontal and the vertical dimensions of this structure. This deserves a bit of attention. So let's take a simpler case where we have fewer particles. This is the notation that DETO is using. DETO starts creating particles in the position 0, 0, in the origin of the x and y axis. It assigns a given diameter, which you specify here, to the particle, d, and then it creates another one next to it, again with the diameter z, and then another one, another one, another one, another one, etc. So eventually, the size of the system that you are modeling will be NELX, which is this input that you're giving here, the first argument, times d. And the position of the last particle, the horizontal position, will be 1, 2, 3, 4, 5. It will be NELX minus 1d, the horizontal coordinate. Okay? And then if you add half and half diameter, overall the length is NELX times d. Then for the second layer, the particles are arranged in a triangular fashion. So the first top particle will be in between the two leftmost particles. The second one will be here, third one, fourth one, fifth one, sixth one. So as a result, every even line, so this was row number 1, which contains in this case 3, 4, 5, 6, 7 particles, where 7 is what we call NELX. In our case, there would be 40 of those. The second row only has 6 particles. It has NELX minus 1. The third row goes back to the same as the first one, so another odd row will have the same number, 7 particles. And it keeps going, okay? So again, there will be an even row with only 6, and so forth. Now, one thing that you have to pay attention to is that if you want to fix a certain height, in our case we wanted to fix h equal 60 millimeters, how do we do that? Well, it's not simply the height of this system is not simply h is not equal simply to NEL y times d, so the number of elements in y direction, this 23 in the example on the top left here, times d. It's not. The position of the second row is d times cosine of 30 degrees, because this is an equilateral triangle, so the angle here is 30 degrees, so cosine of that. The cosine of 30 degrees is d times square root of 3 over 2. So the height h is actually equal to NEL y times cosine of 30 degrees times d. Therefore, from here, if you know NEL y, you can compute what is going to be. So if you know h, you can compute NEL y as being equal to h over square root of 3 over 2 d, which in this case, with this being 60 millimeter, turns out to be 69 over d. 69 millimeters over d. So if we keep reading this line, here we will work with a case where we used particles with a diameter of 3 millimeters, which is correct because then 40, the number of elements in x direction, times 3 millimeters will give us 120 millimeters. So because we want 120 millimeters in our case, we have to use a diameter of 3 if we want to use 40 elements. So this will give equal 120 millimeters, which is what we wanted as a horizontal direction for our system. So 40 NELX, a diameter of 3 implicit millimeters, you have to remember what units you're using, but you don't have to give the units to the code. Whichever unit you use is fine as long as you are consistent. This means that in the vertical direction you have to do, for this example here, if you want to get a 60 millimeters high, you need 69 over d as number of elements in y direction, and with a d of 3 millimeters, which we found from the horizontal direction, we need 23 rows of particles, so that's why there is a 23 here. And finally, the mass. We have to attribute a mass in whatever units you're using. I'm using grams in this example, so I'm assuming it's going to be 3 grams. To be honest, when you will run the simulations, this mass will not be too important because it will be what we are going to do are quasi-static simulations without gravity, and therefore the mass will not count too much. But it's still convenient to put a reasonable value, not a completely crazy one, because there are some parts of the code that use the mass for certain calculations. So it's better if you put a sensible value, even if it is not perfect. So going back to our initial notes, what we have done so far in the code, we have specified how many particles we want to put in the horizontal direction, how many rows of particles we want to have in the vertical direction, remembering that one will have NELX, second one NELX minus 1, NELX, NELX minus 1, etc. How many particles rows we want in the vertical direction, we call it NELY here, the diameter of each of these particles, and the mass of any of these particles. So far we've filled this whole rectangular domain correctly with particles. Now the second step is that we want to attribute to each particle an initial value of this existence parameter xi between 0 and 1. And in this case, like I mentioned, we attribute to all particles an initial 0.3 uniform. So this comment here is telling you initialize xi uniformly, so all particles have the same value, give it a value of 0.3. There is also a way to read these initial values of xi from an external file, so that you don't have to start necessarily with all the particles having the same xi. This will be useful later when we will use the result of a first simulation to get additional results. Then we will start from a file and we will not start from an initial distribution. And the syntax to load it from a file is given here, but we will use it in a later example.